Okay, now it's
okay. So I guess so. You can see the screen, right?
Okay. So
Perfectly.
welcome to Mr. Tyomkin, who will tell us about numbers associated to the barcode of a strong Morse function.
Thank you very much. Thank you very much for inviting me. It's my pleasure to speak here. So, and the last, I hope, technical question is, can you see now the dashed rectangle? You do, right?
Yes, we can.
Great. Okay, right. So let me start. Thanks again. In case you have any questions, please interrupt me at any time you want. I hope to be broadly accessible. So, okay, let's start. So first of all, I want to give the special thanks to Vanis Tupkowski for letting me know that the daylight saving time exists. Because when we scheduled this meeting, it was before the mid-March. So, and I was thinking till lately in my local time terms, and it was incorrect, a bit incorrect. Okay, so thanks, Vanya. Right, so I'll continue. So what I'm going to be talking about is a joint work with my supervisor, Petya Pushkar. It's going to be right about the numbers on the barcode. On oh wait, you don't see my face, right? Oh, that's terrible. That's now you should. Okay, so it's about, well, basically one object and its properties. And so basically the numbers on the barcode of a strong Morse function. Right. So here's the plan. So first I'm gonna define what is an enhanced barcode. So the barcode with these numbers is what we call enhanced. So then I'm gonna talk about its basic properties. Then I will end up with the twisted coefficients and Reidemeister torsion, which is kind of more advanced properties. And then if I will have time, there are sort of several options to end up with. Okay, so let's start with the very first one. So first I'm gonna set at the stage for the whole talk. So let F, big F be a field. So in this yellow boxes, there is something that you may not want to care about. So this is some auxiliary remarks, or I mean some additional material. So if you they're not really crucial for understanding what happens. Right. So in the first two parts, so here and there is one only cares about Q and ZP, but in the third part, they're going to be other fields are going to be useful. So first, the basic definition, which we will be playing around to the end of the talk, is called enhanced vector space. So vector space over F, vector space over F is called enhanced. If I choose the following two structures, first, a full flag on V, right? So a full flag of subspaces, and second, a non-zero element kappa S in the quotient, right? So this is the one-dimensional vector space, and I choose its generator for all the possible S. Okay, so and this second part is what it really is all about. Right. So once I have this algebraic structure, I may define two functions which depend on V small, which is a vector. So for V, this V small is as a non-zero vector in V. I can define its height, which is the minimal S such that V belongs to Vs. So you simply consider all your subspaces, and you look for the first one where V small appears, and this is called the height. So quick in the naive sense. And second, the coefficient, the coefficient of V, this baby, is lambda and f star. This is all the elements of the field which are non-zero, such that PS of V equals to lambda kappa S, where PS is a projection to the one-dimensional space, and VS maps like this to VS quotient by VS minus 1, where S is HT of V, right? So if I have the vector in my vector space enhanced, I can always project it to this successive quotient, right, where the S is taken to be height. And this is the element in the one-dimensional vector space, and I already have one, right, this kappa S, so I compare two elements of the one-dimensional vector space to get a number, lambda, and this is what I call the coefficient. Cool. So any questions so far? Yeah, that's good. So now let me proceed to the geometrical story. So let M be a closed manifold, F a Morse function. We call F strong if all the critical values are pairwise distinct. So what I mean by that is that, so well, there are critical points and critical values, and I don't have and any two critical points have distinct critical values. So this is the generic condition, which is crucial to our constructions. So what I mean by that is that if I change my Morse function, so is I mean in a one parameter family, so that in the beginning it is strong, then it is also strong, but during the path it might be not strong, so two critical values sort of collide, then my invariant changes, I mean the barcode changes, and enhanced barcode a fortiori changes. So that's an important thing. Then to simplify what will follow, let me choose some any regular values R0, Rn of F, such that between two consecutive one, there is exactly one critical value, right? So n here is the number of the critical points. So again, the classical definition is the sublevel set for a real number A. I can define the sublevel set MA, which is all the points of X of M, such that f of X is less or equal than A. So I mean the sublevel is understood in the usual sense, which we think about the Morse functions as the height functions. So if you have the height functions, everything which is below is a sub-level set, right? So have the usual good old theorem that MRS is homotype equivalent to MRS minus 1 plus a k-dimensional cell, where k is the index of the S critical point. Okay, so I hope this notation is clear. A bit, I mean, a bit many letters, but I hope it's okay. So for the technical reasons, I also have to define what is the oriented Morse function. It's not that important as any time with orientations. I mean, you have to say about them, but you don't really care. So F is called oriented if the generator of this homology group is chosen, right? So this, you see, it is just the homology of this, I don't know, the relative homology of this space over Z is Z, but it's non-canonical Z. You have to choose, you have two choices of generators. So let me choose one for each S. And then this is called the oriented strong Morse function. But by default, as usual in this stuff with precision homology, I'm going to be talking I'm going to be taking homologies over F with coefficients of F. So these are F vector spaces, right? So I'm done with the stage. Any questions on the setup? No.
I mean, when you say all homology is taken over F, in the line immediately before that, you took homology with Z coefficients just for the
right. Yes. So I mean,
so in other words, if F is Z mod 2, you still really want an orientation.
Well, if Z mod 2, no, I don't need orientation. No, I mean, I can choose one, surely, but it won't affect my numbers.
Okay.
As you will. So if I'm writing the field of coefficients, like here, I'm in F. If I'm writing them explicitly after this I don't know, after this comma, but the point, then I mean that's explicitly Z, right? So I'm going to proceed to the definition of the and how, I mean, the definition now a.k.a. So what I want, right? So I have defined what enhanced space is. It is a vector space. Now I have this many geometrical like stuff like M and F small, and I'm going to construct enhancement on HK on M, considered as a vector space over F, defined by the Morse function F, right? So that's my goal. I will now accomplish it. So let iota S. Let iota S be the map induced by inclusion, by the standard inclusion of the sublevel set MRS to M. Okay, so this is the inclusion of topological spaces. We have the induced map on homology. It may be not an injection. It's some arbitrary map. We consider it, and we consider all the images of this iota S for all the S's. Right. Again, S is from 1 to dimensional V. I mean, well, here it is from 0, but it's 0, so it doesn't really matter. Right. So just embed all the sublevel cells into my big M and consider all the images of the iota S, and this is clearly defines a full flag. So what I mean by this is that, I mean, the image of iota S may or may not increase. I mean, it's a sequence of vector subspaces. So we only care about the dimension. So the dimension may or may not increase. But if it does increase, it also increases by 1, right? At most by 1. So I look at all the time where it increases and say, okay, the dimension of this image has increased. Good. I'm taking this new subspace as my flag space. Okay. So I've done with the first part of the enhancement. Okay. So if my dimension has increased right here, S equals to so then I have to look at the a priori long exact sequence of vector spaces as associated to the pair MRS minus 1. So it is, a priori it is long exact sequence, but in this case it is a short exact sequence. So right here L/S, meaning that, right? So in this case, this is the surjection. This is actually maybe check to be injection. So this, so the long exact sequence just cuts out to being short. And this is just embedding. Can you hear me well? Can you hear me well? No?
I think it's okay. I mean, your sound cuts out now and then, but I think I think you as the speaker should ignore it. We can hear, we can put them together. So it's okay.
Okay.
Just keep going.
I might try to pull them out and try as all right. So is it better now or not?
It suddenly got much better just in the last
Great,
15 seconds.
great. I mean, is there any problem?
Now it's bad again.
No, yeah, no, it's bad again.
Please,
It's quite
please.
bad, yeah.
please tell out loud. No, right. So that's probably because of the internet. So okay. So I guess I should just try to continue, right? As the David said, right? Yeah. Okay. Great. Okay. Good. So okay, maybe switch off. No. Right. So this. So and now I have this JS, my maps, which map my homology into big M, into the homology of all M. And so what do I do now? I note that this vector space is isomorphic to this the Z tensor F, and in this F I have this one, right? So this is Z tensor F, but I have chosen the generator of this Z. So formally I have to consider this this one one element in one-dimensional vector space. So I mean that it is that this isomorphism with F is canonical. There's a preferred generator. Okay. So morally, you should think of this generator as the class of the attaching cell. So have this excision isomorphism, right? In this rectangle, and with this isomorphism, there's a preferred generator of the fundamental class of this sphere, and this is what I'm talking about. Okay, so here I take first any preimage of this one under P. So this is the surjection onto the one-dimensional vector space with the preferred generator. I take the preimage. It is, I mean, I take any preimage, and then I take iota s, the image under the map to HK of M. This is some element defined up to something, but its class is well defined in my in the quotient, in the successes quotient of my flag. Yeah. So you remember that I defined the flag to be the images of this iota s's, and this element kappa s doesn't depend on the preimage chosen. Well, it's simply because of the exactness of this sequence, right? So if I lift anything by I mean with respect to P, then this the lift depends on the kernel of P, which is the same as the image of this map, right? So the ambiguity lives in the image of iota s minus 1, which is precisely what I want. So here I have defined kappa s, right? Okay, good. No. Okay. Okay. Right. So so the crucial note is that, I mean, it's badly viewed, but this also defines enhancement on each HK. So let me write this down. Defines enhancement on each HK of M of RS, right? So not only on the homology of all the space I have this enhancement, but also on all the sublevel sets, right? So simply by restriction to the RS, I have this segment, and I'm going to really use this right now. Okay. So then I'm going to do the definition of the enhanced Barannikov decomposition. Right. So in our paper we use the term Barannikov decomposition, but this is precisely the same as the barcode. So since the people are more used to this term barcode, I'm going to use this term during the talk, right? So what is it? This starts with the thing that you all know or heard about it, is that first, it is the decomposition of the graded set 1 to n of critical points, right? It is graded by the index of the critical point. So and also I might say either critical points or values, because these are in natural bijection since the function is strong, into 3 disjoint pieces called upper, lower, and homological. This is the first kind of part of the data of the enhanced barcode. Second, the bijection B between the sets from U to L of degree -1. So I mean that the degree of B of S is 1 less than the degree of S, and also we have this BS less than S. And third, I mean the kind of the dramatis persona of this talk is a map from U to F star, right? So I mean it is precisely the number on each bar, right? So, for example, in this picture, we have this is the upper, this is the lower point. These two are homological, and we have these numbers on each bar. On each bar. And now I'm going to define this in terms of out of the function. Okay, so I'm given m, small f, and a field, and I construct enhanced Barannikov decomposition as follows. So I fix 1s, just as usual, the number. Now I consider another term of the already mentioned exact sequence. So here I considered this this projection, but now I want to look at the kind of next map, which is the differential hk of mrs to which maps by differential to hk of mrs -1. So if it is non-zero, I mean, if it's 0, I don't care. If it's not, I'm gonna do the following. So I'm gonna put s in u, right, under this decomposition. Second, I'm gonna put ht of d of 1.
I'm sorry.
So I have this one, the distinguished element.
You hear me?
Right. Okay.
So again, what are U and
yes.
L? I somehow didn't hear it.
Okay. I'm sorry. So U and L are 3 disjoint subsets.
Yeah.
U, L, and H are 3 disjoint subsets of this set.
Right.
Of this set of all
critical values or points,
from 1
right?
to n. And I'm not.
Yeah, and they represent what?
He's telling us right now how you get.
Okay. I thought I somehow missed it. Okay, thanks. Sorry.
No. Yeah, I'm defining this right now. Okay, so I have this one in this vector space, the generator of the one-dimensional vector space, and this one, and then it maps to by d into this space, also vector space, right? So I have this d of 1. It is some non-zero element in the enhanced vector space, right? So when you're given a non-zero element of the enhanced vector space, you know what to do. You have to first take its height, and then I'm defining b of s as its height, and I'm going to set lambda of s to the coefficient, to its coefficient. Okay, with respect to the enhancement on hk on m r s -1, right? So is that clear? So in this case, this s. Okay, so let me on this picture. if I encounter D,
So if the critical point is of index K, then
yeah, right. Right. It should be K minus 1. Thank you. Right. So for example,
basically, like you have some critical point. Critical points are numbered 1 up to n, so they're basically identified with their number,
right.
1 up, which is also height.
Right.
So the 1 up to n refers both to height in this thing and the actual name of the critical point. So the cell is put into U if it has non-zero boundary, and then in that case, its image, which may be a complicated mix of lots of things, its image may be a sum of lots of
right. But it was an index K cell, right?
So then you put that index into L.
Yes, okay. Exactly. Right.
and
Thanks
then
for
lambda is this map only on the upper ones, and that's reads off the coefficient. And the coefficient was how much times your fixed generator was supposed to be.
Yes, right.
The value on the upper thing is how much times the fixed generator, the image boundary of it is. Okay.
Yeah, right.
And you have not told us the bijection yet, right? You have not told us the bijection B yet.
Here it is. The bijection B is this
I see.
B of F.
Sorry. Yeah, right. Okay, right. Good.
It is the height. So the height is some number. It corresponds to some critical point. So I pair of this 2, and then the coefficient is the 2.
And then H is everything else.
Yes, right. I'm sorry, I didn't put this on the one else. Right. Everything is H is all the rest. Yes, which didn't get into U or into L.
So let me see that you go into U and L when the attaching map is exactly hitting the previous cell, right, of 1 index lower. Is that what's happening?
Well,
so that you can cancel them. Is that basically what's happening?
You get into L if you get into L if you're the top highest cell, which is the boundary of some other cell, right?
So it's like
are you pairing the critical points you can cancel? Is that what's happening?
No, not really. I mean, you can cancel critical points if in order to cancel the critical points, there were strong geometrical conditions.
Right, but these are algebraic conditions for canceling.
Well, in a way, yeah. So you can say that you can actually cancel them geometrically, but this is kind of, yes, algebraic conditions.
This is algebraic conditions for them to be possible for canceling. Okay.
But like if lambda is 5 or something.
In a way.
You might be able to cancel them, unless I'm missing something.
Say again?
Like if lambda is 5 or something, if lambda is something other than plus or minus 1.
Then you're definitely unable to cancel them. Yes.
Right.
Yes. So for them to be able to cancel it out, you have to have lambda either 1 or minus 1. If it is not, then there is no home.
Yeah, right.
Then there is no home. But actually, I mean, the geometrical situation is much more subtle.
Right.
Okay. So here is upper.
But also, if they were going to cancel, they had to be paired into U and L, right?
Yes, right. So usually you cancel out 2 points which are neighboring,
right?
Which are kind of close to each other. And for this to happen, they have to have this number equals to plus or minus 1.
Plus or minus 1, yeah. Okay.
Okay, great. So everything except for lambda was initially constructed by Barannikov in '94, and very similar construction of these numbers. I mean, in a certain sense, was done by Lepedrec, Mir, and Viterbo in 2000 and 20. Right. So this decomposition does depend on f. Let me stress this out. So you take not only the function but also the field, and if you change the field, then this decomposition also changes. I mean, the points of f obviously don't change. So you have all this. So this the linear order on the points stays the same, and the indices stay the same, but the pairing and the numbers do change. Okay, so now I'm going to turn to the first properties of this construction. Any questions? Not yet being asked. Okay, great. So the properties. So if you're given a Morse complex, so this is the so for this to happen, you have to fix a metric. Note that I didn't fix the metric yet, and I will not do it. But if you're given the metric and you're lucky enough to understand what the Morse complex with respect to the metric looks like, then there's kind of sort of simple linear algebra which allows you to extract these numbers. Right. So first, if the dimension of M is at least 4 and F is either Q or is it B, then there exists a function F on M strong Morse such that there is a pair with any number lambda given in advance. Right. So in a way, there's no control over a fixed bar, right? So it can be any. You give me the lambda, I give you the function. If the dimension is big enough, right? So this orientation business is really not that big. So if you change the orientation of f, it may only affect the sign. So if you change the orientation of either this point or this point, then this 5 changes to -5, and nothing else happens. So, I mean, canonically, you have all numbers defined up to ±1. This is the second property. The third is this funny low-dimensional thing that this. I mean, by p -1 pair, I mean the pair which has index p for the upper point and index p -1 for the lower point. So the set of 1, 0 pairs. So the pairs which have index 1 upper and index 1 lower, and the set of n -1 pairs, if m is orientable, doesn't depend on f. So this is the statement about the usual barcode, the usual well-known hyped barcode, and all the numbers on such pairs are ±1. So that's kind of, there's not much happening. For example, on orientable two manifolds, there's no non-trivial numbers at all. But you see, if the dimension is big enough, then there are. And the fourth property, again, it doesn't consider numbers. It's just some the stuff about the barcodes, that the dimension of HK of M equals to the number of homological points of index K. Okay. Right. Any questions? No? Everything's good.
I have a question. So if over Q you have one of the lambdas equal to 5, does that guarantee that if I then work over Z mod 5, there will be fewer things in U and L and more, like that there will be 5 torsion in the homology, or is that not the case?
Sorry, I didn't get the very last words you said.
So if I have if I get a lambda equal to 5 when I work over Q, is it the case that if well, I guess, is it the case that there was 5 torsion in the Z coefficient homology, or in other words, does that mean?
No, it doesn't. Wait. I think it is. It may not be so. I'm not sure. I'm not sure, but I think it may not be so because of, for example, you can have not 5, but no, like 1 or 3. So in this case, it is a question: what do we want to say about integral homology? But for Q, you can always find at least one pair on which the lambda is integral. This is kind of a funny statement.
Oh, wait, so you're saying? Okay, so lambda sometimes is not an integer over here.
Right. Yeah. I mean, this is, you see this statement. So if you give me any lambda for f equals to q or z.
Okay, I guess that is apparent from year 1 now that I reread it. Sure.
So I can find a function which has, I mean, at least one pair with this number.
Interesting. Okay.
Right, and so after the second thought, right? So it's definitely, you can't say that if you have 5, then there is 5 torsion in the homology of M. It doesn't have to do anything with homology of M. I mean, yeah. So you can't make any consequence from this fact. Okay. So now I figured it out. Right. So I still have some time left. So let me define this. I mean, this is the definition of this some number. The number is defined as follows. I call it tau, which stands for torsion, but torsion is heavily overused. So I'm going to say just tau. Just a number in f star, which is the product of all the lambdas, but possibly taken into the power -1, depending on the parity of the index. So if the index, well, we see the formula, if the index is 5, then I have to take lambda to the -1, because I mean 5 is odd. So I have this product. Well, it might be called alternating product, like an alternating sum. So this is this tau, and the slogan, which I'm going to be advocating to the end of the talk, is that tau is worth looking at since it connects barcodes with the theory of torsions. So barcodes is one theory, torsions is another one, and to the best of my knowledge, there is no yet there's no connection written in the literature, but actually there is, and it is done via this tau. So this slogan has 2 incarnations. Well, actually 3, but I'm going to talk about 2 of them. The first one is quick. The second one is heavy but richer. So the first one is this theorem, which I'm going to state right away. So read it from there, right? Theorem. So suppose M is an F homology sphere. So the manifold, which has the same homology over F as the sphere, and F is a strong Morse function, then this number up to psi is independent of F. So as we know, if I change some orientation on the cell, the number lambda may change. So I am unable to keep track of the sign, and I don't want to do so. But if I quotient out by sign, this product doesn't depend on F. So it was kind of surprising for us to discover. So okay, that's also when you see that something doesn't depend on F, the natural wish is to define it without F whatsoever. And this may be done. I'm not gonna do it now, but it can be done. So here tau, well, as you can see, may be expressed as a certain torsion with respect to some basis in homology, whatever that means. Right. So the first example that one the continuous is M equals to RPN, and if F being equal to Q, the rational number, so this RPN is a Q homology sphere. And so in this case, tau equals to plus minus 2 to the integral part of n over 2. And on RPN, we also have the standard Morse function, which gives the standard cell decomposition. And in this case, the barcode looks as follows on the right-hand side. So, well, actually, I mean, this is the barcode for the RP6. If you want to, I mean, to get the barcode for RP5, you have to just cut out this picture at the level you want to, and then you get the barcode of your RP5, right? So it looks as follows, and from there you can see that indeed you just multiply all the numbers, all this choose to get this number. Right. So actually, this is the first example of the non-trivial number on a pair, right? There's 2. Okay, so I have 3 minutes, 7 minutes to go for the richer example, but I mean, any questions? Maybe. So it's better to understand less, but better. No, it's okay. Right. So now we'll try to speak about twisted coefficients Reidemeister torsion. So first, I wanted to. So I actually still want, but I'm unable to, I guess, to go rigorously through this construction of the Reidemeister torsion. So R here is for Reidemeister torsion, and this is a purely topological thing. If there's a nice invariant of a manifold invented back there, 100 years ago, it doesn't have anything to do with the Morse theory. So let me be, I don't know, the quickest, but the quickest I can. So I have to take M, well, a manifold, but I mean, actually the topological structure is enough up to homomorphism. You have this P is pi 1, pi or is pi 1 of M. You have the group ring, this of pi 1. It is the ring. So I have the map of rings from 0 of pi 1 to F, some field, and such that the homology vanishes. The homology with this twisted coefficient vanishes. The output is some number in this quotient I don't know, group, right? So I have pi sitting in 0 of pi. You might take its image under the row. It will be some subgroup, and then you divide it by the factor out by this subgroup. You have a number called the Reidemeister torsion. Well, how do you do it? Well, I guess I'm gonna skip this at least for now, because well, so it is a purely topological construction. How do you proceed? Well, so I'm sorry, but I guess it's better to skip this for now. Right. So what I'm gonna to say, yeah, the first and marvelous example of this of the usage of the Reidemeister torsion is that it distinguishes length spaces, whatever that is. So length spaces are some topological spaces which are homotypic equivalent but not homomorphic. So the usual invariants like homology are unable to distinguish them, but the Reidemeister torsion is not invariant under homotypic equivalence. It is an invariant of homomorphism, but it's not an invariant of the homotypic equivalence, which is good in this case. This is vital. And then what can we do? How do we proceed? So we consider twisted enhanced barcodes. So what is an enhanced barcode is already defined what it is. The twisted is the following. So given M, a manifold and a function f on it. Again, I consider this map of rings rho from 0 of pi to m. And I claim that it's possible to construct the twisted enhanced barcode out of this data, regardless of the homology being 0, right? So as I previously said, the barcode always exists, enhanced or not. But if the homology is 0, then this number is interesting. Okay. So what would be again? So the situation here is kind of the same as with the change of fields in the previous parts. So the points of an instance of the barcodes are going to be the same, but pairing and numbers may change after this twisting. And this time numbers live not in F star, but in F star mod out by this rho of pi. And the theorem, which I want to, which is kind of the highlight, is that if I'm given the manifold M rho as here and F such that H star such that the homology vanishes. So it is precisely the setting where the Reidemeister torsion is defined. So I look at this Reidemeister torsion and it coincides with the product of all the alternating product of all the numbers on the barcodes on the bars considered in this quotient ring. And in particular, this tau again doesn't depend on F. So there's some way to express the non-invariant called Reidemeister torsion in a through the numbers on the barcode, through the numbers on the bars in the barcode of F, right? So this is the second incarnation of the slogan that I'm advocating, right? Of this slogan, this up over there. So the kind of the informally, if there's no homology or almost no homology, then this number doesn't depend on the function. So individually, all the numbers, individually the number on each bar is uncontrollable. You don't have, it can be any, but the alternating product of all of them is sometimes does not depend on F. And the easy statement is here for the homology sphere, and more advanced statement is right there for Reidemeister torsion. Right. So boom, 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 boom. So it all looks less important when there is 1 minute left. I'm sorry. Right. Okay.
I mean, hold on. I think you have more than a minute left. Am I right, Mike?
Well, I mean, for questions, I mean, the rest is for questions.
Yeah,
the rest
okay.
is for questions, I guess. So, so let me stop here. Thank you very much for letting me speak. Yeah, well, the very last interesting thing is that Asher and Zhang defined the barcodes of the Markov field, which is useful in the in the Floer theory and symplectic topology. This is the heavy work which deals with the what they called non-Archimedean SVD decomposition, purely algebraic cool stuff. And the work in progress is to translate these numbers into their settings. So take the campus of the Markov field and then try to assign again some kind of numbers to these bars. Right. So now I'm happy to answer questions or maybe speak about something more. I don't know. Up to you. So thanks for listening. Thank you very much.
Questions?
I'm really sorry for the sound. I have to,
It actually got a lot better shortly after we were having problems. I guess maybe your internet connection improved. So I'm curious about, like, can you explain how you get a third as a number in some examples? It's sort of I don't know, I find this a little surprising.
What? A
So,
third?
so how does it happen that you can get non-integers as these lambdas?
Oh yeah, okay, yeah. This is so I have to give you a complex, which is so how do I do it? Right. So let me do the following. So let it be complex like right like this. So it can be, I know, like any so these two indices are the same, k minus 1, k minus 1, and so this is think about it of this as the Morse complex, right? So it's not a Barannikov decomposition or barcode. This is the Morse the Morse complex with respect to symmetric. So it is claimed that it's possible to to use the good old handle sliding to obtain, I mean, and I fix all the orientations. So this is 1 1. This can be any integer. Yes. So if you do I mean this, if it's a and this is b, then you can do the handle slide to find out the Morse complex, which looks like this one in the different bases, which looks like a plus 5b, right? And for this, and you see, now I'm appealing to the handle sliding technique, which only works if the dimension is at least 4. So if the dimension is at least 4, then for k equals to 2, then f dim. Well, I mean, k has to be at least 2 or and no greater than dim n minus 2, right? So this is where I'm using the dimension this restriction. So here we
Can I
have this.
just ask something? What should I think about this 5 as representing that I'm gluing on like some 5-fold cover down to the previous generator, or is that how I should think of 5?
You mean this 5 is your
Yeah,
Morse
the
complex?
5 that's in your graph.
Yeah. So simply a Morse complex. So you might think of it as that there are 5 gradient flow lines from A to C, with the all being counted with ones, with plus signs, right? So this differential actually counts the gradient flow lines with signs as usual.
Okay.
So this is kind of and but this barcode is not interesting in the sense of enhancement for this. So this is the Morse complex, and the corresponding barcode is going to be written down there. Enhanced barcode. It's simply this 1 and 1. But now what do? I do the nasty thing. I'm gonna switch A and B. So I'm gonna consider the path of functions, which switches the critical values A and B, right? And the Morse complex doesn't change, right? So this eraser. So now I'm considering another another function, which is almost the same, but the two generators swapped. So now the complex is, the complex itself is the same, but the linear order on the generators has changed dramatically. And now what the barcode looks like is, there's a bifurcation. Which happened? This 5. Until now, these are 2 in pair. This is 5, and these 2 are in pairs. Also. The uppermost and the lowermost. And here it should be it should be -1/5. So you more or less don't care about the minus. I mean, it is interesting, but not today. But the thing is that you see, actually, there is a kind of effect when two paired paired critical points swap in this linear order like this. Tau doesn't change. Tau doesn't change, right? Regardless of any homology being 0 or not, it is always true. So always, always, right? Doesn't change. This is kind of a funny effect, right? So you see that this in tau, this two lambdas go with the same power, like if k is odd, then it is -1. So previously the product was 1, and then we know definitely for sure that now the product has to stay the same up to sign, everything up to sign. So now there's 5 and this is 1/5. So this kind of how you get this statement that any number is possible. So here it is, Michael.
Great, thank you. Any other questions?
Yeah. So my question is, if you you seem to know a lot about how this changes when you do elementary moves, swapping, and so on. Is there any? Have you thought about whether you can get some like return maps? So if you have a circle of Morse functions, then you get some interesting invariance of loops of Morse functions.
Yes, exactly. Well, this is actually what you said is the third incarnation of this slogan. So 2 of them I have already said, and the third is kind of maybe not that right, but still exists. So what is it? So what is it about it? It's called Akhmetyev Repov-Zenzel theorem. So what is it about roughly? So consider the serve diagram of a path of functions. So now ft is a path of Morse functions, generic, I mean, which starts and ends at the strong Morse function and paths of functions, Morse functions. Long. So okay, and now what you can do after you learned about Morse theory is to learn about serve theory, and this, and kind of you might want to first of all, the good curiosity is to find out how this changes. This Barannikov
Are you
function.
allowing to go out of strong Morse functions so that
exactly right? So any sort of diagram. So both this cusps dying and both are allowed, and this self intersections.
Right. Yeah.
So,
Okay.
So this is non-strong Morse, non-Morse functions, and this is not strong Morse, not strong functions, right? And it is interesting to find out, I mean, how this form changes, and this was already done by Barannikov, and there are some funny pictures like this one, like this one, and so it is actually a rich subject. So if you axiommatize what's happening during this one parameter bifurcations, then you end up with the definition of the ruling of the Legendre knot by Pushkar-Chekhanov, and by Pushkar-Chekhanov. I guess in English it's Chekhanov, Pushkar. Chekhanov, yes, Chekhanov, Pushkar, and Fuchs. So if you just say, okay, I know how the Barannikov form changes along the path, I want to take any serve diagram, well, basically any front of the Lejanian knot, and just find out, like formally, purely combinatorially, what is the number of the possible, say, pairings between this such between the arcs. Then you and if you kind of roll out this thought, then you arrive precisely at the rulings. So what is interesting here in the terms of the enhanced stuff is that this time this torsion actually, I mean, this, so in serve theory you consider the path of functions where each ft is not on any m, right? It is on m times 0 1 to 0 1, which is a constant on this zero part. So and you have to consider the relative Morse complex and stuff, but what you end up with is that HFT is a function on the cobordism, on the trivial cobordism m0t m cross 0 1 m cross 0, right? So each ft is kind of this, and the Morse complex counts this homology, which is always 0 for any, I mean, it is homology equivalence. So the homology of this is 0. Homology is 0, I mean, over z. So in this case, you may define this torsion, this tau lives in z2, which you have to think of it, well, I mean, as a k1 of z. I mean, so usually torsion lives in some k group, but if you take a field, then k1 of a field is f star. If you take the z, then k1 of z is z2. And then there is this Akhmetyev-Repov theorem that puts, I mean, so this there is a certain restriction on serve diagrams, on, or I would say on oriented serve diagrams, in order for them to realize, as an honest path of functions, right? So if I give you the serve diagram, then, I mean, like formally, just any picture which looks like this, I don't know, right? So then the question is whether it's possible to find an honest path of functions which serve diagram looks as this one. In this formulation, it is always possible. I mean, well, for dimension of, I mean, for any for m like equals to Rn or something, or sphere of big dimension. But you may consider what's called an oriented serve diagram, which is a certain choice of orientations up to changing. So I mean, that's I don't have much time to say about it, but oriented serve diagrams actually come up naturally from the path of functions. So it is natural to consider them, and it turns out that not all the oriented serve diagrams realized. There's a certain equality mod 2 which has to be satisfied in order for the oriented serve diagram to be realized. This is the content of this Akhmetyev-Repov theorem, and we have a proof of it which works in more generality. So they proved it like for dimension of m at least, I don't remember, either 4 or 5, and in some other cases. And we have the proof of this theorem which works for any manifold. And this done precisely in the same manner. This is done via analyzing what's happening with this tau, which now lives in Z2 in the path of functions. So it is a useful context. So here it is.
Great, thank you.
Yeah, so I guess we maybe can take a break and return for tea, if that makes sense. I forget how we usually organize.
So we clap one more time and then I'll pause the recording.
Yes, we could.
Thank you very much. Thank you very much.